Well, I made the graphing of membrane potentials a separate talk because it's just a little different concept. Still an important one, but I think getting membrane potentials is kind of its own thing, and then translating that into a graph, which is not a real natural sort of process for us, adds another layer of challenge. But it's important in the medical setting. I mean, you've seen this, right? That kind of tells you somebody's alive. Well, that has its roots in these membrane potentials, especially action potentials. So they do become pretty important. Let's take a look at how to graph membrane potentials. Well, I recommend, not only just at first, but as you continue, to never separate the graphing from what's going on in the cell itself. I think that's important. But as long as you take your time and really think about what's going on in the cell, I think the graph will come a little bit easier. This is a little bit like sort of the tediousness of working out Punnett squares. If you take your time and dot all your I's and cross all your T's, then the outcome is a sure thing. This one's a little bit trickier, but let's start with how the cell is set up. So remember that the inside of the cell, notice I've drawn it like a banana here, is rich in potassium, just like bananas. Outside the cell, and we're only concerning ourselves really with the ions that could move in and out if we were to open up some channels. Outside the cell, of course, is sodium, but there's also a bunch of other stuff outside the cell too. So we also have calcium ions with their 2+ charge. We have chloride ions with a negative charge, and we even have bicarbonate ions with a negative charge. Point here is, don't worry about memorizing all this stuff. Potassium belongs in the cell, everything else belongs outside the cell. Now there's a one exception. Calcium in muscle cells is locked away in the sarcoplasmic reticulum, so you'll find lots of calcium in little pockets, but not floating around in the cytoplasm. Remember, we're only talking about just movement of ions only across the membrane. That's it. All right, so now we have our cell set up. To then look at the graph, y-axis is potential, the membrane potential in millivolts. And usually we're looking at changes over time, kind of like that heart monitor graph. I drew it first, but this is going to be a weird one. 0 is going to be up toward the top of the graph usually. So that's pretty strange. We're used to down here being 0, 0, not in these membrane potential graphs. So that's 0, but what's the normal charge of the membrane at rest? Yeah, -70. So I'm just going to make this bottom -100, and this is -70. So if a cell was just at membrane potential, resting membrane potential, it'd probably vary just a little bit, but it should basically be right around -70. Not a good sign if you see that on a heart rate monitor. It should be going up and down. But for most of our cells, they kind of hover around -70. Maybe there's a little blip where they use some of that energy and go towards 0. But that's kind of the typical graph. Well, let's give ourselves some ways of talking about the graph and the membrane and kind of merging these two into a common set of terms. Right now, this membrane has a negative charge inside and a positive charge outside. We've seen that a bunch. That's called polarized, right? So a covalent bond had a positive and a negative. We call that polarized. North and south poles, they're two different areas. Polarized membrane. So at -70, our sort of starting point, we can call that polarized too. So there we go. That's polarized. That's kind of normal for the cell. Well, what if we started changing things? Because that's when all this would apply, right? If we started changing the situations in a cell. What if some of these positive ions came into the cell? Well, now we're bringing positive ions in. Would that make the inside of the cell more positive or negative? Obviously more positive. That's a pretty easy one. So if the inside of the cell is becoming more positive, on the graph, would that go up or down? It would go up because this is a negative number, and so that is in a more positive direction. Does that make sense? I hope so. So that's going up. That would be what would happen if these positive ions came into the cell. Let me ask you a little harder question, terminology-wise. If the cell started polarized, is this becoming more polarized or less polarized? Well, it's going towards 0, so that seems like a bad thing. 0 would be not polarized at all. That case, the cell would be dead, so that's not good. So this is becoming depolarized. So if that membrane potential goes up, if positive ions enter the cell, then it's depolarizing. Let's think about a slightly different situation. Same cell, same graph. But what if instead of a positive ion, what if this negative ion were to enter the cell? Well, that would make the cell have a more negative charge inside the membrane, right? Makes sense. So more negative on our graph, that would be this direction, be even more negative, had more potential energy, changing it from the resting state. So it's obviously not polarized, it's more than polarized. And for this one, we call it hyperpolarized. So hyperpolarized. So that's kind of the terminology that tells you what happens in the cell can be represented on a graph. Let's try a couple different scenarios. I've taken away all your clues about where everything is. You're going to have to remember that. Let me give you this scenario. Let me put it on the graph first. Right here at this time, we're going along, cells at resting membrane potential, -70. And at this point, we open up a calcium ion channel. So cell has all kinds of different channels, and some of them actually have little lids that can open and close, essentially. So this one just opened. What would happen? Let's walk through this one just one step at a time. First, where do we find calcium mostly? Outside or inside the cell membrane? Should be outside the cell. More concentrated outside the cell for the most part. Therefore, if we open up a channel and let calcium move through, would it move into the cell or out of the cell? Sure, move down the concentration gradient into the cell. So our next question is, how does that affect the charge across the membrane? Because we had a positive outside, negative inside. What does that do to the inside of the cell? Yeah, it would make it more positive because it's bringing positive ions in. And calcium with 2+ charge is pretty powerful, so the cell becomes more positive. So now that we understand what's going on in the cell, what does that look like over here? Does it go up or does it go down? Yeah, it would go up. And if we close that channel, then it would level out here. And if we then pumped calcium back out, then it would return to the resting membrane potential. That's good. Let's try a different one. All right, so same basic setup on the graph. At this point, we open a potassium channel. What is that going to look like on this graph? Where the cell started at resting membrane potential, -70 millivolts, then that opened. Again, let's go through the process. Potassium, inside or outside the cell? Where's its highest concentration? Okay, inside the cell. So we open up a channel, and then is it going to leave or more come in? Should leave down its gradient. And what does that do to the charge? Positive charge outside, negative charge inside. So it's a little bit trickier. We have positive charges inside, and they're leaving, kind of like money leaving your wallet. The cell is going deeper into debt, so actually it's left with a more negative charge as more positive ions leave. Well, that makes the graph pretty easy, right? It becomes more negative. It hyperpolarizes. So there's some good practice. This sets us up to understand the graph on an action potential. Not the emphasis in this class, but I think an early peek at it would be a good idea. Let's take a look. All right, well, this cell is different. This is a neuron. They're long, narrow cells, so this is the upper membrane, lower membrane, and it would continue either direction for a long time. So we're only looking at one small piece. I'm going to hold my tester just right here. Right? We're only looking at this area of the membrane. And the way this works is once the voltage changes, these channels, one for sodium and one for potassium, are triggered by a voltage change. Once the voltage gets up to about -55, then those channels spring open. So that's what they do. And they're staggered. The sodium channel opens first, and the potassium channel has a slight lag, and so it's going to open second. And so we're going to assume that basically here we reach that -55 and trigger things. And then we'll look at what happens for each of those channels. Well, first, sodium channel opens. Sodium comes into the cell, positive ions, depolarizing it. So it's going to go way up here, up to like +30. So crazy, big change, big change. And then time 2, right after that, this opens. Potassium leaves, essentially reversing what just happened. And now that membrane potential comes crashing back down. Stays open a little bit longer, so it actually polarizes even more. And that's kind of it. Once they're back down here, these guys close up again, and now the sodium-potassium pump has to start spinning and pumping sodium out, potassium back in, and over a little bit of time, then it gets back to -70, and it's ready to go again. There's the action potential. Sodium floods in, potassium floods out, everything closes up, and it goes back to normal. Now, to move this down the line, we only did something here. These membrane potential changes would then trigger these to open because they would create a small change to the membrane potential, trigger these both to open, and the next ones, and the next ones, and the next ones. And that's how the action potential spreads down the neuron at a couple hundred miles an hour. Now that you understand how to graph these and how the cell is set up, hopefully you follow that. If you're in my class, I'm not expecting you to reproduce this. That's for Anatomy and Physiology 1. But I think it's kind of exciting that you can understand what's going on and look at this and say, that makes sense to me. If that's where you're at, perfect. Graphing is just kind of one of those necessary scientific skills. Not only being able to construct a graph, but being able to interpret it as well. We're asked to do this all the time. And it summarizes a lot of information in one small package. So this is just more good practice at interpreting graphs. Until next time, keep appreciating life, even if you have to graph it.